Can you see the pointer? Okay.
Yes, we see the arrow. When you,
okay, so
now it's red. Yeah, okay, now it's red point. We can see. Okay.
Okay. So let's start. Thank you for introduction. I'm Ryuna Nagayama from the University of Tokyo. Today, I'm going to talk about thermodynamic trade-off relations and optimal transport for reaction diffusion systems. This talk is based on this preprint. Maybe as you know, reaction diffusion systems describe chemical or biological pattern formation such as fish or BZ reactions. And despite long-standing effort, thermodynamics cannot predict where a pattern will go. For example, thermodynamic quantities such as dissipation generally provide no Lyapunov functions for 3 pattern. However, thermodynamic quantities may reflect the detail of pattern change, for example, in the form of thermodynamic trade-off relations. So we can use this reflection to evaluate energetic efficiency of pattern formation or chemical systems. So today's goal is to answer this question. How does dissipation reflect the detail of the pattern formation? Here, I quickly introduce the setup of our study. We consider the deterministic reaction diffusion systems and focus on the evolution of internal species, which do not interact with outside. In simple case, time evolution of the concentration distributions in reaction diffusion system is given by such simple reaction diffusion equation. However, we consider more general case where the diffusion is described by the general current, and reaction is described by the reaction current. Then we can write the time evolution by continuity equation for the concentration distribution of internal species. Here, X means the internal species. We also write stoichiometric matrix by using this transpose of gradient form for some mathematical reasons. And our results do not depend on how the system interacts with the outside. The central quantity we focus on is the entropy production rate. Using thermodynamic force, we can write EPR as the inner product of current and force. In addition, we can rewrite this inner product to the quadratic form of thermodynamic force like this, with the metric induced by the relation between current and force. In general, we can see the linear relation between diffusion current and diffusion force with positively finite mobility tensor. For example, in simple case, we can obtain this tensor as such very simple form. However, we consider more general case. And in addition, we can construct the linear relation even far from steady state for reaction part based on the detailed balance condition. Under this local detailed balance condition. Under local detailed balance condition, the thermodynamic force is this form, and we can obtain this matrix. So the diagonal component is a log mean of forward flux and reverse flux of reaction. Then we obtain the metric by abbreviating this matrix or relation. Then we can decompose entropy production rate into 2 non-negative parts via Pythagorean theorem, because now EPR is a quadratic form of the force. In particular, we can extract the necessary part for time evolution from total entropy production rate by projecting the equilibrium force, this equilibrium force, onto the subspace of force, which reproducing the original dynamics of internal species. And then we can obtain the orthogonality as a necessary condition for this minimization problem, and we can decompose the entropy production rate into 2 non-negative parts. And the first term of 2 negative parts, quadratic form of this optimal force, is excess entropy production rate, which is the minimum dissipation required to reproduce the original time evolution. And the remaining part is housekeeping entropy production rate, and which is caused by current that does not contribute time evolution. We can obtain this decomposition far from steady state or without steady state. And this decomposition is a generalization of the excess housekeeping decomposition originally considered by Mas and Netsucheni in this paper, and developed in these papers in stochastic thermodynamics and thermodynamics of chemical reaction networks. In our preprint, we also provide the new decomposition of entropy production rate into non-negative contributions corresponding to Fourier mode by using the generalization of Pythagorean theorem, so Parseval identity. But yeah, I will skip this part. We also generalize the Wasserstein distances to reaction diffusion systems to measure the distance between patterns consistently with thermodynamics. In original optimal transport theory, we obtain the distances between probability distributions by calculating minimum transportation cost. Therefore, we can obtain some distances between patterns by considering minimum cost of reaction and diffusion. Specifically, we generalize the 1 and 2 Wasserstein distances which are used in stochastic thermodynamics. The 1 Wasserstein distance for reaction diffusion systems is obtained by this minimization problem, which is a minimum cost flow problem, which is a generalization with a Beckman problem. Which is this is one expression of 1 Wasserstein distance. And we also can generalize 2 Wasserstein distance to reaction diffusion systems via Benamo-Brenier formula, which is the well-known expression of 2 Wasserstein distance. And this corresponds to minimum dissipation problem because this part is the same as entropy production rate. This is important point. Anyway, these distances are distances between concentration distribution of internal species. Then we can obtain thermodynamic speed limits by combining the Wasserstein distances and excess entropy production rate. By measuring speed of time evolution with Wasserstein distances like this, and defining reaction diffusion intensity appropriately like this. By measuring the speed of time evolution like this, we can easily check the speed of time evolution measured with 2 Wasserstein distance is the same as the square root of excess entropy production rate. And we also can obtain the relation between these 2 speeds like this. Then, taking time integration of these relations and use the Cauchy-Schwarz inequality appropriately, we can obtain 2 times of thermodynamic speed limits. So let's see the detail of thermodynamic speed limits, these ones. So the thermodynamic speed limit with the 2 Wasserstein distance shows that if we want to make the speed of change in pattern be faster, we need more dissipation, because if the speed is faster, the lower bound is larger and larger. In contrast, the speed limit with the 1 Wasserstein distance helps to capture the elements in a more broken down manner. So we can see that if we want to make the speed of change in pattern be faster, we need more dissipation, or we need stronger reaction diffusion intensity. In this simple numerical example, the first bound, so blue one, is tighter than the second one, red one. But I emphasize that we can also construct some processes where the second one, red one, is tighter than blue one by considering the condition of equality of the Cauchy-Schwarz inequalities, which is appearing in the derivation of these speed limits. In addition to thermodynamic speed limits, we can also obtain thermodynamic uncertainty relation, TUR, which is a generalization of this previous study. So in this previous study, they consider the thermodynamic trade-off relations for chemical reaction networks, which is not reaction diffusion systems, but we can generalize the result by introducing the conjugate operator of generalized divergence and using this special potential function. Then I explain the detail of TUR. TUR is this form, and the denominator of the right-hand side includes 2 contributions. And the second contribution is the kind of the indicator of fluctuation of reaction, and it does not depend on the wave number. However, the first term depends on the wave number, and in simple case, this term reduces to this form, and if the wave number is larger, this denominator becomes larger. So this trade-off relation means that we need more dissipation to change in the coarser structure, which corresponds to smaller wave number components. Finally, I summarize this presentation. We answer the question how dissipation reflects the detail of pattern formation by thermodynamic trade-off relations obtained by generalization of techniques in stochastic thermodynamics, such as decomposition of entropy production rate, or the connection between optimal transport and stochastic thermodynamics, mainly studied in these papers. That's all.